All right, today's lesson, lesson 5, linear models. We're going to do line of best fit with technology. So, this is actually a 2-day lesson, had it been done in the classroom. 1 day to go over the information and another day to complete the assignment, which would mostly be done in class, but you'll be doing it at home. I'll still be giving you 2 days on it. So previous learning, we did lines of fit, which for that you would plot your points. You'll visually pick 2 points, make a linear model, and use that to make predictions. Now, as you should know, based on correcting previous assignments, your line of fit is usually a little bit different than my line of fit because we pick different points, so we come up with different equations. Now, line of best fit is using intensive calculations to find the best line that is statistically closest to the available data. It's kind of like finding the measures of center that we did in 7th grade to describe a population, although it's much more exhaustive in the calculations. Because the calculations for the line of best fit are very, very tedious, we will be using technology to assist our calculations. Now, there are various ways that we could do this. A graphing calculator with a statistics engine. That's a very good way of doing it if you have a graphing calculator. I also like to use Microsoft Excel. That's my favorite. But not everyone's going to have that. We are going to be using Google Sheets. With Google Sheets, it's a little bit limited compared to what Microsoft Excel can do, but it will work, and the way it displays things isn't quite as good. But you will have access to Google Sheets and not necessarily the other technologies. So the line of best fit is also called the regression equation. Has 3 outputs that we will be interested in. It's going to give us the slope and the y-intercept, and it will also give us something called r squared, which is the square of the correlation coefficient, which we're going to have to square root it to get the value of r, the correlation coefficient. So the correlation coefficient, I'm going to talk about that for a couple of minutes. So more about the correlation coefficient r. It is between -1 and 1. A negative coefficient corresponds with a negative correlation. So if it's between -1 and 0, it's a negative correlation. A positive coefficient corresponds with a positive correlation. And if r is close to 0, the correlation is not very good. If the absolute value of r, or the size of r, is close to 1, that means it could be 1 or -1. Then the correlation is very good, generally. So here you can see negative correlations down in the negatives, no correlation in the middle, and positive correlation. Now, no correlation does have some size to it, and I'm going to show you some examples to give you an understanding of why no correlation is not just 0 itself, but it's a little bit of a range both sides of 0. So let's look at some examples here. Here's some examples of regression lines and the correlation coefficients that go with them. So this one was done in Microsoft Excel. Microsoft Excel, I've had it output an equation right here, y equals 0.7x, and this says r squared is 1. I square root 1. I get a correlation coefficient of 1. So on this one, this is the absolute maximum correlation coefficient that you can get, 1. If you have a correlation coefficient of 1, it is a perfect correlation, which means these are all exactly linear. Not going to happen very often. The types of things that would do this would be if you were to compare the radius of a circle to its diameter. The diameter is always going to be 2 times the radius. It'll be in a perfect straight line. Okay, next one. This one, again, done in Microsoft Excel, it spit out this equation, and it gave us an r squared of 0.8713, We square root that, we get our correlation coefficient of 0.9334. Now 0.9 is really close to 1. This is a very good, strong, positive correlation. And you can see that the line that has been drawn, which is specifically that line of best fit, which is statistically calculated, is really close to a good share of those points. Okay, moving on to this next example, you see with a correlation coefficient of 0.8, it's a little smaller correlation coefficient. By the way, to get that I had to square root 0.6551, which is the r squared they give us here. Notice that with a smaller correlation coefficient, the dots are more scattered than they were the first time. In fact, this one has a little bit of an outlier to it, but the correlation coefficient is still pretty good, 0.8. Okay, the next one, without the line drawn here, we would probably say this has no correlation because they're scattered a little bit. In fact, it almost looks like, well, we could go this way, we could go that way. It's hard to come up with the correlation on this one where it's no correlation. So generally, if it's below 0.3, it's usually going to be considered no correlation. And this one with a correlation coefficient of 0.1982, it's not very good at all. In fact, if you were given this scatter plot, you would probably say no correlation. Okay, here's some negative regressions. Now this first example, if you notice the correlation coefficient is exactly -1. That's because these points are completely linear and they are going with a negative slope. If it's got a correlation coefficient of -1, it is a perfectly straight line with a negative slope. And that's all you need to remember. If it's got a negative correlation coefficient, it's just a negative relationship. And then the size of the number, ignoring plus or minus, tells you how good the correlation is. So this one right here, Microsoft Excel spit out this equation with this r squared. We of course square root 0.8659 and we get the correlation coefficient of 0.9305, which that's a really high correlation coefficient. So this is a really strong correlation with all of the points being very close to the line. And of course it's negative because it's a negative slope. If we move to the next one, this one's a poor correlation. It's below 0.3, so we would most likely call it no correlation. And it is spread quite well. If we were to draw a line, we probably wouldn't have drawn this line. But this is the statistically best line of fit. It's just a really poor correlation, 0.24. Okay, moving to the next one. This one was about as bad of a correlation as I could create. I was just randomly creating these with Microsoft Excel. And you can see the r squared here is 0.0012. This is about almost as bad as it gets. So the correlation coefficient comes out really close to 0. It's just a little bit less than 0, negative 0.0346. And as you see, that's pretty much no correlation at all at that point because of how close it is to 0. And you know, this one, if it's below 0.3, it's generally poor enough that we would call it no correlation. So in general, let's go back to this. In general, and this works for positives and negatives, between 0 and 0.3, we're usually going to say no correlation. Between 0.3 and 0.5, it's weak. It does show a bit of a positive correlation. 0.5 to 0.7, it's moderate. It's looking pretty good. And from 0.7 up to 1, it is good to very good. And if it is right at 1, it is a perfect correlation. So the correlation coefficient does give you an idea of how good your correlation is. Now let's take a look at, we did the scatter plot lab last week before spring break. These are the regression lines from the scatter plot lab. Now the first, head circumference versus wrist size, I've personally looked at that one and thought, well, that's no correlation. Now, if you run it through the technology, this is using Microsoft Excel, which is my preference. It does give you an equation for the line of fit and a correlation coefficient squared, your R squared. If we square root the 0.1509 and then just round it, we get 0.3885. Now this one is above 0.3, so this is a weak positive correlation, but it's reasonable to go ahead and say no correlation. It's probably slightly positive just because of these two here, which are almost outliers in the group. Okay, here was the height versus head circumference. This one looked a little bit stronger into a positive correlation. Now, if I were to draw a line here, I would have drawn that line there. But because of these points here, it pulls the line in that direction. Because that's what the calculations, and they are rather intense calculations. Right here, we've got 20 dots. If you were to sit down and calculate that by hand, knowing how to do it, which I don't know how to do it, I'd have to look it up, it would probably take upwards of an hour to do it with 20 dots. The computer can do it in less than a second. So generally computers do get used. So there's that correlation. Now the last one, height versus arm span, had a really strong correlation. All the dots tend to follow this dotted line you see. And when we square root the R squared, we get the correlation coefficient, which will be positive, of 0.9269. That is a very high correlation coefficient. It's getting really close to 1. This is a really strong correlation. By the way, this one even seems to make sense. If body parts are bigger, then other body parts tend to be bigger as well. So if you tend to be taller, you tend to also have greater arm span. There are sometimes outliers. People down in this area, they're quite tall, but they have relatively short arms. That's kind of your T-Rex looking thing. And there would be people that might be not very tall, but have rather long arms, kind of your monkey or chimpanzee with the long arms and compared to their height. But those sort of outliers do exist. They just tend to not be the norm. Most people will be somewhere along this line. And notice the slope of that line is really close to 1. Now I think when we did it on my answer key, the equation I got here was, I believe it was this. It was 1.202x minus 33.125. Now notice 1.202 is very close to 1.1751. And negative 28 is close to negative 33. So this was my line of fit. Compare it to the line of best fit. It's pretty close. The line of best fit, though, is statistically the best match for the data given. Now, if you add more dots to it, you'd have to recalculate it, and you'd get a new equation. So more data is better. It just takes longer to calculate. Actually, since you're using a computer to calculate it, it doesn't really matter how long it takes to calculate. Okay, next I got to introduce you to a vocabulary word that you should understand. It's causal. Causal, it's the adjective form of the noun cause. Now, two variables are causal if changes in one causes changes in the other. So I want you to consider these two situations. Does changes in the time you spend walking cause changes in the distance you walk? Well, yes, this one here is causal, because spending more time walking does cause greater distance walking. Okay, next one. Ice cream sales, as they increase, the people at the beach also increase. Well, thinking about this one, does an increase in ice cream sales cause people to go to the beach? No, it does not. Does people going to the beach cause an increase in ice cream sales? That one's a little bit more likely, but still it doesn't. This is not causal. They do correlate. There is a correlation, but it's not a causal correlation. Sometimes when it's not causal, there might be a third variable not plotted that's causing both of them. Or it could just be that somehow they relate, and that's just interesting. So on this one, ice cream sales versus people at the beach, what I would say that causes both of those would be warm weather. As the weather gets warmer, it would cause both of these to increase. Now, there doesn't necessarily even have to be a third variable. Things can still correlate. And you might see something like this on the news at some time, where they will compare the weather for, well, maybe not on the news, but someone making fun of the news. Well, the news does this too. They'll compare the weather for a month with, I don't know, some sort of politicians' poll numbers, and say that as they do better, the weather got warmer, and as they did worse, the weather got worse. But that's just coincidence. There's no cause-effect relationship there. Okay, next I'm going to demonstrate how to do a scatter plot, find the line of best fit using Google Sheets. This will be available for you to look at as well. It's going to be provided in the assignment. Okay, so we've got the example here, which will be done on your copy, and task 1 and task 2 that you will complete. So example, the latitude of a place on Earth is the measure of its distance from the equator. Do you think the relationship between city latitude and its January temperature? Well, what do we expect to be the relationship between a city's latitude and its January temperature? Well, let's think. Latitude is how far north it is. So north of us, you go up north, you get Idaho, there's Montana. You've got the Midwestern states like Wisconsin. It gets pretty cold in the winter there. If you move south, you're thinking about Florida, Texas. It's fairly warm in January compared to here. So I think that the farther north a U.S. city is, the colder it will be in January. I expect that southern, I guess that doesn't need capitalized, southern U.S. cities are warmer than northern U.S. cities in January. Okay. Hopefully you kind of have the same conclusion there that I do. That is what I expect to see when we analyze this data. Below is a table containing latitude and January mean temperatures for 15 U.S. cities. We've got Albany, New York, Albuquerque, New Mexico, Anchorage, Alaska. That's pretty far north. And then all the way down through here. I'm not going to read through all of them. We're going to make a scatter plot of the data. Now this is what you're going to need to do with your assignment. To make a scatter plot, you need to highlight your data. Now if you highlight the column title as well, that will actually help. Now next, we're going to go to Insert. We're going to insert a chart. And this would be similar if you were able to do it in Excel as well. It would be a chart. So that's kind of all over the place. I don't want a line graph that this shows. So I'm going to change it to a scatter plot, which is right here in my suggested. Now if it's not in your suggested, scatter plots, you just scroll down and there's scatter plot. and that's what we want. Okay, and the nice thing is, as we well, I'm going to go ahead and highlight it and move it over to the side so I can still see the table of data. Alright, there is my scatter plot. Now, before, I thought that the further north you went, the colder it would be in January. So the latitude, this is how far north you are, and it does look like as you go further north, the temperature does tend to decrease. Okay, so after creating the scatter plot, you need to do the regression equation, find the line of best fit. So if you've already closed it and it looks kind of like this, you can go back into editing the chart right here with the triple dot, and we're going to edit the chart. Now we're going to customize it. There's a lot of things you can do here and customize the chart style. You can change the font, the colors. You can change a lot of things. But what we're interested in doing for creating a scatter plot is to go into series. Now in series, this is where you can actually change the color. I'm going to leave it blue because, you know, January is cold and blue's a color you associate with cold. Alright, let's see. If you scroll down here under series, we're going to make a trend line show up. This is your line of best fit. And the computer calculates it very quickly and it plots it. Now we don't just want to be able to see it, because if that's all you do, well, now you see the trend line, but we want to know the equation of that trend line. So going to customize series. After picking trend line, we do want it to be linear. There are other options, but we're only dealing with linear right now. And we're going to label it with the equation, and we're going to show the r squared for that as well. And now when we close that, now this is one gripe I have with Google Sheets. Microsoft Excel gets it right, graphing calculators get it right, but Google Sheets does not get it right. But I'll tell you how to interpret it so that you can still get it right, even though Google does not give you things accurately. It's supposed to be an equation, and you know, people at Google are pretty smart, but this is not an equation. It is an expression. Negative 1.76x plus 103. There is no equal sign in there. It is not an equation, it's an expression. But it does give us the r squared. So let's do some work with that. I need to make a scatter plot of the data. I'm going to say that I'm done with that. Okay. I want to make that red. My answers I'm doing in red. Find the line of best fit. Okay. We need to put a y equals in this, even though they don't have a y equals, but we put in a y equals, and then it's negative 1.76 x plus 103. Okay, that would be my equation for the line of fit. Use your equation to predict the January mean temperature. Let's see. Oh, I haven't, oh, where'd things go? There we go. It doesn't say to here, but because we'll end up doing it on the others, I'm going to go ahead and do it. What's the correlation coefficient? Okay, the correlation coefficient, what you'll do there is you need to take this correlation coefficient squared, r squared, and square root it. So I need the calculator. Calculator, there we go. And we're going to take 0.859, and we need to square root it, and we get 0.9268. I'm going to go with that. 0.92268. So my correlation coefficient is, well, actually, this does have a negative line. There are two square roots to every number, the positive and the negative. So the correlation coefficient here actually is the negative 0.9268 because this is a negative correlation. You will have to remember to do that when calculating your correlation coefficients. C. Use the equation to predict the January mean temperature in Juneau, Alaska, which has a latitude of 58.38 degrees north. So we're going to have to do negative 1.76. I'm just typing that on my calculator. Times 58.38. Then I'm going to add 103 to that. Okay, so this is what I calculated on my calculator, and it came out to be 0.2512. I'm just going to round that off to, well, looking at my other temperatures, they were rounded to the nearest tenth, so I'm going to round it to the nearest tenth. So we would expect 0.3 degrees Fahrenheit. Okay, next. D. What would you expect to be the latitude of a city with a January mean temperature of 15? Okay, if 15 is our January mean temperature, then we're going to do 15 for Y, and our January mean temperature is negative 1.76 times X. X will be our January mean temperature, and then plus 103. Now we need to solve that to get X by itself to find what we would expect that latitude to be, and that would be subtracting 103. 15 minus 103 is negative 88. And then we would divide by 1.76. Negative 1.76. And that gives us X equals 50. So we would expect that the latitude, or sorry, the latitude of that city to be 50 degrees north. Latitude. Yeah, 50 degrees north. I guess I should do these in complete sentences. That's what I want you to do. We expect the temperature to be 0.3 degrees Fahrenheit. We expect the city, let's do a better thing here. I'll go with what is in the example. The average January of Juneau should be about 0.3 degrees Fahrenheit. Here we calculate it to be 50 degrees north. A city with a mean January temperature of 15 should be about 50 degrees north. What was your conjecture about the relationship between latitude and temperature correct? I have relationship spelled wrong here. Okay. Was it correct? Well, I thought that it was going to be further north you would get colder temperatures, and that's exactly what it was. So yes, the farther north you go, the colder it gets. And that's what the data shows here. Okay. Now this will be available for you to look over as you're working through your problems. There are 2 problems. There's a worksheet that explains it as well, but it is all right here in Google Sheets. The first one, it shows the number of hot chocolates sold at a coffee shop for 8 randomly selected days, comparing to the high temperature. And you're going to make a scatter plot. Put your scatter plot here in the pink area. Cover up the pink rectangle. And then you are going to answer each of those questions. Leave your answers in red so they stand out. And on the second task, we've got a grade percentage versus an NWEA score, which is what they did before they did the SAGE test. We're doing the RISE test now, except this spring the RISE test has been canceled due to COVID-19. And there's some questions you'll answer there. Please answer in complete sentences. And thank you for watching.